So here's a fact. If a matrix, if it has a row or a column of all zeros, then its determinant is 0. And why is this true? This is just if you use the cofactor expansion. So why is this true? This is because the determinant is computed. Well, the determinant can be computed by cofactor expansion along that row or column of zeros. So that means that you'll be doing 0 times something plus 0 times something plus 0 times something, where the times something are the determinants of the submatrices of dimension lower. And so this clearly says, you can just clearly see that the determinant will therefore be equal to 0. So if you have a row or a column of all zeros, the determinant is 0. So this is an obvious fact. But there's a consequence of this. So one consequence is that if a matrix has 2 rows that are proportional, then its determinant is 0. And why is this true? Well, in the previous video, we talked about the effect of performing elementary row operations. So if you have a matrix, it's like, for example, if its row is A, B, C, it doesn't matter, and then you have another row that's like 2A, 2B, 2C, and let's just stop like that. Nothing else really matters. What we can do is we can perform the elementary row operation, where we subtract, say, 2 times. Anyways, if we can perform an elementary row operation, then we'll get this thing here. Because the 2 rows that I wrote, these are proportional. There's this one, and if you just double all the entries, you get that. So you can perform an elementary row operation, and that gives you all zeros. And we talked about how that this elementary row operation, where you subtract one row from another, doesn't affect the determinant. So we saw that in the previous video. We know that that the determinant of this matrix here, A, B, C, 2A, 2B, 2C, whatever, is the same as the determinant of this matrix here, A, B, C, 0, 0, 0, whatever. And so, indeed, since we end up acquiring a row or a column of all zeros, we see that this determinant is indeed 0. So these are important things for you to just recognize. If you have a row or a column of all zeros, then the determinant is 0. If you have 2 rows that are proportional, then the determinant is also 0. Okay, here is another. So here's just a theorem that the determinant of a matrix, say A, is the same as the determinant of the transpose of the matrix A. And this is true. So this is an important theorem. So this is just because to calculating the determinant, you can do a cofactor expansion along any row or any column. So, you calculate, determinant is calculated. It all comes down to this cofactor expansion along any row or column of your choice. And you can convince yourself that if you, for example, if you cofactor expand, say, A along, say, its first row, this is the same. You can see that, you can just see that this thing here is the same as if you were to cofactor expand A transpose along its first column. And therefore, so these two things are the same. And of course, the way you would actually calculate the determinant is you do this cofactor expansion, and by definition that gives you the determinant of A. And over here, if you do this cofactor expansion, by definition that gives you the determinant of the transpose. So we see that they're actually the same. So that's a very important result, that the determinant of a matrix is the same as the determinant of its transpose. So in particular, a corollary of that, just combining everything, is that if a matrix has two proportional columns, then its determinant is 0. Okay, so that's just putting everything together, because then its transpose, so the explanation is since then its transpose will have, because in the transpose the rows become columns and vice versa, so its transpose will have proportional rows. So that implies that the transpose, that you'll get the determinant of the transpose is equal to 0, but that's equivalent to saying that the determinant of the original is also equal to 0. So that's just putting everything together, since, then its transpose will be proportional. Sorry, my handwriting is especially bad today. So let's just go back one more time. So if a matrix has a row or a column of all zeros, then its determinant is 0. This is an important fact, the consequences of which we are investigating now. So this fact here implies that if a matrix has two proportional rows or columns, then its determinant is 0. There's also this result, and this we could have just shown right away when we introduced the cofactor expansion for calculating the determinant, that the determinant of a matrix is equal to the determinant of its transpose, and that implies that if a matrix has two proportional columns, then its determinant is 0. So you can summarize this by just saying this and that, saying that if a matrix has two proportional rows or columns, then its determinant is 0. Okay. So what are some other properties? So this is a very important property here, which is that the determinant of a matrix is equal to 0 if and only if A is not invertible. And then not invertible, we call this thing singular. Let me rewrite that. So we'd say that A is singular. So this gives us a way to determine, so this is a very important result here, this allows us to determine, so we can use this to determine whether or not a matrix is invertible. Because, as you know, it can be very tedious to calculate the inverse of a matrix. So you don't want to waste time trying to calculate the inverse of a matrix if there is no inverse of the matrix. So you don't want to waste your time if it can't be done. So it's good to just first determine whether or not you can calculate the inverse, whether or not the inverse exists. If it does exist, then you can work on trying to calculate it.